This video is simply a recording of a presentation that I delivered to a VHF amateur radio conference in October of 2018 on the basics of Smith charts. So what is a Smith chart? It's really a graphical tool to help you plot and compute a number of things, such as complex impedance, complex reflection coefficient, voltage standing wave ratio, and transmission line effects, as well as helping you to design RF matching networks. And there's certainly much more that can be done with a Smith chart. So let's break it down. First thing we need to talk about is normalized impedance. The complex impedance that we plot on the Smith chart is done with what we call normalized impedance. Normalized impedance is when we take the actual measured impedance and divide it by the system impedance. In most cases, that system impedance, or Z0, is 50 ohms. So we're essentially going to divide all the values by 50 ohms. So in the case of a complex impedance value of 37 plus J55, we divide both of those values by 50 to get our normalized impedance, and we'll call that Z prime. So in this case, Z prime would be 0.74 plus J 1.1. This makes the Smith chart usable for any system impedance, whether maybe a 600 ohm impedance system, a 75 ohm impedance system, or like I said, in most RF applications, it's a 50 ohm impedance system. And this normalized Z prime, or this normalized impedance, is what we plot on the chart. So let's take a look at some of the important regions on the Smith chart. The center axis, or prime axis, is the purely resistive axis. So any points lying just on that axis are where there's no reactive component at all. The region above that axis, that hemisphere, is where the reactive component is inductive, and therefore the region below that is where our reactive component is negative or capacitive. Let's look at some key values on the Smith chart. Right dead center is our system impedance. So in our 50 ohm system, that center point represents 50 ohms. All the way over to the right, along that prime axis, is open circuit, where essentially infinity. And then obviously at the other end represents a short circuit. The circles on the Smith chart you can see are all kind of tangent to the infinity axis, represent constant resistance, or normalized constant resistance. So the one that passes right through the center of the Smith chart is the normalized resistance circle, a value of 1. There's the constant normalized resistance of 3, constant normalized resistance of 0.4. And if you look carefully along the center axis, the Smith chart, you can actually see these values right along the circles. So we can see there's 1.0, 1.2, 1.4, 1.6, etc. So that's how you can figure out the values of these constant resistance circles. The arcs that are all emanating from the open circuit position are the constant reactance arcs. So we've got in this case, here's our constant inductive reactance of 1.0, and the constant capacitive reactance of minus J1.0. And you can see here's plus 0.5 and minus 0.5. And again, if you look along the axis at these labels for these arcs, you can see what those values are. And of course, if there is no reactance at all, essentially you're right back onto our constant resistance line, or prime axis within the Smith chart. So let's plot a complex impedance. Let's start off with a complex impedance of, say, 25 plus J40. So we know it's inductive. We're going to be above the center axis. The first thing we need to do is normalize that by dividing by 50. And that gives us a normalized complex impedance of 0.5 plus J0.8. So what we do is simply look for the intersection of the resistance circle of 0.5 and the reactance circle of 0.8. And if we follow those along and we find the point where those intersect, that plots that complex impedance on the Smith chart. And oftentimes when we're designing a matching network, we're going to be adding elements like inductors and capacitors to create a matched circuit. If we add elements in series, we're going to move along the Smith chart curves in a certain way. So we typically will add these components to essentially drive our complex impedance down to the desired point, which is the system impedance. If we add series inductors and series capacitors, we're going to move along the constant resistance circles. So for example, if we add a series inductor, we're going to move clockwise along the constant resistance circle. And we can see if we move, for example, from this point to this point, we essentially added, in this case, 0.6 normalized reactance to our measured impedance. Series capacitors move us counterclockwise along the constant resistance circles. So what about admittance? It's handy to talk about admittance when we're adding elements in parallel. Now, of course, everything we've talked about thus far is constant impedance. So what do? Well, admittance is really just 1 over the impedance, right? So that's pretty easy. So in a sense that you say, well, the constant or the conductance is 1 over resistance, and susceptance is 1 over reactance. But the reality is those two equations are really only true when the real component, okay, the R is 0, okay? That's the only time we're really going to have that, because otherwise we have to take this complex quantity and invert it. And that's a little bit more complex math. However, converting to complex impedance, or from complex impedance to complex admittance on the Smith chart is really easy. It's a lot easier than doing the math. Let me show you how. So first we start off with the impedance that we plotted on the Smith chart. Okay, and then we draw a circle that's centered at the system impedance, right in the center, that crosses through our measured impedance. And then we draw a line diagonally through the circle, cutting through the center of that circle, and then touching the other sides, or bisecting our circle. And that location that we wind up with on the other side is essentially our complex admittance. So when we just read the values right off the chart from the resistance and reactance lines. So in this case, a constant or an impedance of 1 plus J1.1 is a complex admittance of 0.45 minus J.5 as shown here. So the admittance curves, where are they? Because we've talked about these impedance curves, constant resistance and constant reactance. The admittance curves are really just taking the Smith chart and rotating it 180 degrees. So if we actually just turn that chart around, we would actually have that. Now we can actually just play a trick by doing that, by doing the bisecting that we just showed on the previous slide. But what you'll also find is that you can pick up and find combination Smith charts. In this case, all of the red lines, okay, the red circles for constant resistance, the red arcs for our constant reactance lines, and then the blue lines shown here are all for the admittance, so constant conductance lines and constant susceptance lines. So these combo charts are available to make your life easier if you want to go through and manually do transmission line and impedance matching network computations. So again, here's the constant conductance circles and the constant susceptance arcs. So if we're going to add elements in parallel, we want to use those admittance curves. Okay, so in the case of adding a shunt L or shunt C, we're going to move along the constant conductance circles. So here we can actually see adding a parallel inductor moves along a constant conductance circle this way. Adding a parallel capacitor moves along the constant conductance circle that way. So this is much easier. The easiest thing to do is to use a combination Smith chart to be able to go ahead and do this, rather than doing the transformation that was shown a couple of slides back. It can be done either way, but certainly easier to do with the combo chart. So here's a quick tip, and to remember which direction you rotate in. When you're adding inductors, you elevate through the real axis. So adding series inductors rotates up through the real axis this way along the constant resistance circles, and then adding parallel inductors rotates on the constant conductance circles up through the real axis. So we're elevating through the real axis. Kind of corny, but it works. Well, we can get even more corny and say, well, when we're adding capacitors, we crash down through the real axis, rotate the other way down. We're going down through the real axis with adding series capacitors here, we're rotating down on the real constant resistance circles, and now the parallel capacitors rotate down on the constant conductance circles, rotating or crashing down through the real axis. So a little bit corny, but it's easy to remember now which way we rotate along these axes when we're adding series or parallel inductors or capacitors. A little bit more Smith chart magic, some other detail that's on here. And let's talk about what are called radially scaled parameters. And these are the parameters that you see down along the bottom axis. We'll talk about just a couple of them. There's a number of them there, but we'll talk about the most common ones. So let's say I've got a complex impedance plotted on my Smith chart here. First thing let's do, let's draw like a radial line from the center to that point. Now if we rotate that line up to the real axis, okay, so we just use a compass and draw that up here, and then extend that line straight down to our radially scaled parameters. We can read a number of parameters right off the Smith chart. First thing we can see that is for this particular complex impedance, that would represent a voltage standing wave ratio of 2.3 to 1. Right, we're reading that right off of our SWR axis here. That also corresponds to a return loss of 8.1 dB. Also corresponds to a power reflection coefficient of 0.155 or a voltage or current reflection coefficient of 0.39. So really easy to go ahead and determine those parameters. Now something that's interesting to note is that any impedance that is along this arc, or effectively even all the way along the circle, will have the same SWR. So let's talk about standing wave ratio and transmission lines and how we can relate that on a Smith chart. So again, as I mentioned on the previous slide, we draw a circle around the Smith chart centered at the center, cutting through our measured impedance. What this is plotting out is a whole array of different impedances that will give us the same SWR no matter where we are. Now one trip around that Smith chart, going around the circle, represents a 1/2 wavelength of transmission line length. So what that tells us is that each time the transmission line length is increased by a 1/2 wavelength, we're repeating the impedance. So let's say, for example, I've got an antenna that has a certain impedance, and the transmission line I've got going to that antenna is a multiple of 1/2 wavelengths long. That means that the impedance looking into the transmission line is equal to the actual antenna impedance. Okay, and that will repeat itself every 1/2 wavelength of transmission line. Now, of course, halfway around the Smith chart then is a 1/4 wavelength. Now, what's really interesting here is that you get an impedance transformation that's pretty significant and unique with 1/4 wavelength or odd 1/4 wavelength multiples. Like if I go 1/4 wavelength or 3/4 wavelengths, etc., I get this transmission line or this impedance transformation. And the most interesting one to look at is, let's say the impedance we're looking at was an open circuit. Okay, if I add a transmission line that is a 1/4 wavelength long and that's open circuited at the end, it will look like a short circuit at the 1/4 wavelength point. And vice versa, if I have a 1/4 wavelength long transmission line that's shorted at the far end, it looks like an open at the transmission at the input end. So let's talk a little bit more about that, a practical application. Let's say I've measured a given impedance at my transmitter end of a transmission line. So I've got a transmission line going to an antenna, and I measure the impedance that's seen at the transmitter. Okay, I can use the Smith chart to predict what the impedance is actually at the antenna. So what we can do is use these scales along the outer edge here, and we can see they're scaled that says wavelengths towards generator or wavelengths towards the load. So if I measure a given impedance at the transmitter, and I know the length of the coax to the antenna, or the length of the transmission line to the antenna, I can then predict what the actual antenna impedance is. And once I know what that antenna impedance is, I can then design a matching network that can be placed at the antenna to match the 50 ohm transmission line impedance and therefore avoid transmission line losses. So how do we go about designing L networks or impedance matching networks? The simplest would be an L net matching network. We're simply going to be talking about adding a series or parallel inductor or capacitor to move from our load impedance or measured impedance to the system impedance. And there are different topologies that can be used. So we could add a shunt capacitor and series inductor, a shunt inductor and series capacitor, and vice versa. There's a number of different ways of doing that. Which topology you use depends on where your load impedance winds up being. If your load impedance winds up in this area up here, then that tells us we can use this topology. We could also use one of these topologies as well. Similarly, if my load impedance was down here, I might want to use this topology, okay, or maybe possibly that one, depending on where the load impedance is. The choice of which one you use might be determined by whether we want, say a high-pass network or a low-pass network, or it might be based on what components you have available in terms of the selection of inductors or capacitors that you might have available or that you might have to wind or design. So there may be some other practical considerations that might influence your decision on which topology to use for your matching network when you have a choice of more than one. So again, sometimes more than one topology will work. So let's go take a look at a practical example or two. First, let's look at the process. What I like to do if I'm going to do this manually is start off by drawing the constant conductance circle on the Smith chart, as well as the constant resistance circle for the unity value of conductance and resistance. They're going to help me later when I design the network. Because what we want to do is pick a topology based on where the inductance is, or the impedance is. In this case, this topology is going to work. So I'd start off with, say, a series inductor and then a shunt capacitor. So the first thing we want to do is add the first element so that we rotate around until we hit either the unity resistance or unity conductance circle. In this case here, if we add a series inductor and rotate up until we hit our constant conductance circle, now I've got the right amount of inductance for my net matching network. And then I can add a shunt capacitor to rotate down through the constant conductance circle till I reach my normalized impedance value or my system impedance value. And once I know that, I can figure out how far or how much inductance and how much capacitance I've added and then compute those values. So let's do an example. So the first step we want to do, again, is let's say we're operating at 432.1 megahertz and we've measured an impedance with, say, an impedance analyzer or vector network analyzer of 75 minus J60 ohms. So first we need to normalize that, and that gives me a normalized load impedance of 1.5 minus J1.2. So we want to go and plot that value. So there we have it right here. Now that I've got that value plotted, let's pick a topology based on where that is. And again, for my little yin-yang diagrams earlier, I can see that this topology here, which consists of a shunt inductor followed by a series capacitor, will give us the right values or the right network to bring me from this impedance point to our system impedance, or the center of the Smith chart. So here's how we go about it. So first thing I'll do is I'll draw in my constant resistance unity circle. This will kind of help us later. First thing I want to do is add a shunt inductor. So we're going to rotate along this constant conductance line until we hit that constant conductance circle. So we rotate up and we've got that. All right, now how far did we move? If we take a look at the curves here, if we look at my blue lines here, there's 0.3, there's 0.4. So we're sitting at about 0.32, rotating up to 0. So that's this segment here was adding 0.32. And then this segment here, if we follow the numbers, is adding 0.05. So the total amount of normalized inductive susceptance that we've added is 0.82 ohms. Okay, so if we invert that, that tells us that our normalized inductive reactance is 1.22 ohms, and we multiply that by 50, and that gives us my inductive reactance of 61 ohms, and then we can calculate back from our 432 megahertz operating frequency and calculate back to a inductor of 22.5 nanohenries. So now I know the inductor value for my matching network. Now the next step is we want to add our series capacitor to rotate down to the center of the Smith chart. So if we add that value in there, we can see that I've actually moved by a normalized capacitive reactance value of 1.2. So if we unnormalize that, I've got a capacitive reactance of 60 ohms. And again, knowing our operating frequency, we can calculate a capacitor value, in this case of 6.14 picofarads. So now we've designed a matching network that took me from my measured complex impedance that wasn't matched to 50 ohms, and by adding these two components to it, we now have a 50 ohm input impedance looking into that network. Now this was all done using one of the combination charts, which makes it really easy. Let me just show you the process of what you would do if you wanted to go through the pain of converting from impedance to admittance and back and forth. So again, we would first draw our constant conductance circle, unity circle. We plot our value and the constant SWR circle, because remember the first thing we're adding was a shunt element, so I need to convert to admittance. So we bisect the circle, we converted to our measured admittance. Now that I've converted to admittance, now I want to add that parallel inductor. But because I've rotated everything 180 degrees, when I add that inductor, I'm rotating down along what would be the constant resistance circles, but now we're constant conductance, okay, until we hit my constant conductance line of 0. And then we want to draw another another constant SWR circle around that, bisect again, so now that we're back in the impedance domain instead of admittance domain, and then we can add our series capacitor to get back down. So we're still got the same length of arcs that we showed earlier, and then you can use that to compute the complex impedance values, or complex resistance, or excuse me, complex capacitance and inductance values, and get back to that same matching network. So it's a lot more complex to do it this way. The combo charts make it a lot easier. In fact, there's automated ways of making it even easier yet, but I wanted to show you the mechanics of how all this works. So in summary, a Smith chart is really a very highly useful tool, and probably more so back in the days before computers and before calculators. We could actually solve some of these very complex transmission line impedance matching problems graphically, rather than having to run through all of the very complex math. We can do the complex impedance transformations from capacitance and inductance, from reactance to susceptance and back and forth. We can do all of those transformations. We can do impedance transformations with transmission line lengths very easily. We can determine SWR and return loss and a lot more, and design matching networks and a whole lot more that we haven't touched on. So a pretty brilliant invention that was developed here for doing these complex transmission line type of equations, and that we really didn't touch on them. These days, a lot of this work can be done in an automated way. And what I'd really suggest that you do if you're interested in playing with this is check out a PC-based tool called SimSmith. It was written by another ham, AE6TY, and you can see the link here. And I'll put those links in the video description down below, where you can actually go and download this program. And then also my friend Larry Benko, W0QE, has done a lot of really great tutorials on SimSmith in terms of how to use it and things like that. He's got some examples on his website that's shown here on the bottom link, and he's also got an excellent YouTube page where he's got a couple of really great tutorial videos on using SimSmith that basically can run through everything that I showed you to do manually, but do it in an automated way. And it really takes using Smith charts literally to the next level. So I hope you enjoyed this short little presentation of the introduction to Smith charts, and you got a little bit better idea of what Smith charts are used for. Thanks again for watching.